Hi, I'm Engineer Tolentino. Here's another video presentation of ECA Graduating Batch of 2013 from Polytechnic University of the Philippines, Santa Rosa Campus. This batch consists of shoulder, elbow, and finger. I hope you enjoy watching.
Hi everyone, I'm Jade.
Hi everyone.
I'm Jade.
I'm Yuri.
And I'm JL. We are the PSEC graduating batch of 2013 from Polytechnic University of the Philippines, Santa Rosa Campus. As partial fulfillment for the requirements of the subject thesis under Engineer Tolentino, we are here to present and discuss to you our project entitled Application of Pneumatic Air Muscle on the Abduction movement of the glenohumeral joint robot based on human shoulder anatomy.
The shoulder joint anatomy. The muscles that are involved in abduction movement are the supraspinatus, deltoid muscle, and teres minor. The supraspinatus muscle is a relatively small muscle of the upper back that runs from the supraspinatus fossa superior of the scapula to the greater tubercle of the humerus. It is one of the four rotator cuff muscles which holds the humerus in place and keeps it from dislocating. It also performs the first 15 degrees of arm abduction. The deltoid muscle is the muscle forming the rounded contour of the shoulder. It is made up of three distinct sets of fibers, the posterior, lateral, and anterior. The deltoid is the primary abductor of the arm. It can abduct the arm up to 90 degrees from the torso. Lastly, the teres minor. It is a narrow elongated muscle of the rotator cuff which aids the arm in adduction movement or lowering the arm parallel to the torso. Pneumatic air muscle. Pneumatic artificial muscles, or PAM, are contractile or extensional devices operated by pressurized air filling a pneumatic bladder. PAM were first developed under the name of McKibben artificial muscles in 1950s for use in artificial limbs. The air muscle consists of a rubber tube covered in tough plastic netting which shortens in a scissor action. It pulls like a human muscle when inflated with compressed air at low pressure. The longer the length, the higher the pulling force. However, the strain at high pull force region is much smaller than at low force region. Since air muscles have nearly the same power curve and ability as human muscles, they have a great ability to mimic human motion. Actuator orientation. In placing the actuator, the proponents carefully observe the origin and insertion points of the muscle in the human anatomy to fully satisfy the goal of imitating it. The air muscle is connected just at the top of the revolute system and runs down halfway to the shaft that acts as the design's humerus. In that way, it is easy for the mechanism to execute the abduction movement because it is acting the same way the human muscle works. The proponents use three air muscles that resembles the three parts of human deltoid muscle, the posterior, lateral, and anterior deltoid. The concept of this design is to introduce the use of air muscle in robotic industry due to its muscle-like characteristics. The air muscles are placed in the same way with the human muscle anatomy to achieve the optimum resemblance of the humanoid shoulder joint. In that way, it is easy for the mechanism to execute the abduction movement because it is acting the same way the human muscle works. The proponents use a proportional control system in which a pneumatic valve is being switched on and off in a very fast frequency. The prototype is designed such the angular displacement of the robotic shoulder depends on the contraction of the pneumatic air muscle. Thus, the pneumatic air muscle must be controlled between its maximum and minimum lengths. The way to control the length of the pneumatic air muscle is by proportionally controlling the pressure fed to it. The proponents suggest switching an electro-pneumatic valve in a certain frequency and varying its duty cycle. In this manner, the pneumatic valve will produce a proportional pressure output with respect to the duty cycle of the frequency used to switch it on and off. The proponents investigate the relationship between the output pressure and the control signal experimentally because of some unknown parameters such as the switching delay of the solenoid valve, the nominal flow rate of the valve, and the flow rate of the system. To get the effective pressure of the air muscle, the proponents observe values of angular displacement by controlling the pressure of the design controller and also by controlling the pressure with the manual pressure regulator. In this manner, the proponents can find a function between the control signal and the effective pressure produced.
And that's the end of our presentation. For more videos, click this link. Thanks for watching!